Um, all right, so thanks for the introduction. So in this talk, I will be talking about this wonderful block cipher called the AES, and how we can use a pipeline to get serial modes of operation really fast. This is joint work with Andre and Elmar. So of course we all know this wonderful block cipher called the AES. It was designed by two brilliant Belgians, Damen and Raymond, in '97 for the AES competition. And we also, of course, all know that this was standardized by NIST in 2001. And now we all carry one, if not several, implementations of this cipher in our back pockets. And what can you do with the AES? Well, you can use it for a great deal of things, actually. You can use it for modes of operation, for encryption and decryption. You can use it for block cipher-based MACs, compression functions, hash functions, and you can use it for authenticated encryption. And now, especially with this ongoing CISA competition, we have seen actually several modes of operation using the AES for just that. So I want to take you through a short timeline of how AES implementations have looked like in the past 15 years. Of course, in 2001, we have the table-based implementations that are very much cited by Brian Gladman. And back then, this was running at 25 cycles per byte, which back in those days actually were considered quite fast. 6 years later, we have implementations using bit slicing by Matsui and Nakajima, and this was running at roughly 9.2 cycles per byte. But this is not counting overhead associated with the transposition between the AES representation and the bit sliced representation. So this is sort of adds on top of that. Then in 2008, we have table-based implementations by Bernstein and Schwabe, and these were running at roughly 10.5 cycles per byte. And if we compare against now Gladman's code in 2008, this was running at roughly 16 cycles per byte. Now, another wonderful thing that happened in 2008 was that Intel, huge chip manufacturer, realized that we need to really get very fast AES implementations. So what they did is they came with this proposal for AES-NI, which is an extension of the instruction set to do really fast AES. One other implementation I want to highlight is the Kesper-Schwabe implementation that also is a bit-sliced implementation at about 7 cycles per byte, but this one doesn't involve any overhead compared to the Matsui Nakajima implementation from 2 years previously. Now, if we fast forward a bit, we see that we have seen now 4 different microarchitectures from Intel implementing AES-NI, and the first one was in 2010, the Westmere. And we see that it dramatically increased the performance all the way down to 1.25 cycles per byte. And now in 2013, the latest architecture, Haswell, is running AES at roughly 0.625 cycles per byte. But even with this wonderful AES-NI, we see some sort of a performance deficit actually for the serial modes of operation. So for example, for a CBC mode, we see that this is running at approximately 4.5 cycles per byte, while for the parallelizable modes such as ECB, these are really fast, all the way down to 0.6, 0.7 cycles per byte. So if we look at these two performance figures, we really see that ECB mode comparing to CBC is roughly 7 times faster. So what is the explanation behind this? Well, if we look at CBC mode in encryption and counter mode in encryption on the right-hand side, what we see is, of course, that what we all know, that CBC is serial, so to be able to encrypt, for example, a second message block, we first need to have produced the first ciphertext block. This is not the case for counter mode, so we can perform encryption in parallel. So the obvious question is, what can we try to do to really speed up these serial modes of operation? So this brings me to the outline of my talk. First off, I will be starting by giving a short introduction to AES-NI and pipelining. Then I will be talking about what the packet sizes look like on the internet in the real world. And this sort of motivates the real contribution of our paper, which is the comb scheduling. This is a method to speed up this serial modes of operation using pipeline. And then in the end, I give some performance data to back up the claim that this actually works for our purpose. So if we look at ASNI, these instructions that I already mentioned, Intel brings us these 6 new instructions. So we basically have 4 instructions that perform encryption and decryption, and then we have 2 other instructions for key scheduling. So these are the ones I have written here. And also I want to highlight this multiplication instruction in the bottom. So this does careless multiplication of 2 64-bit operands. And this is very useful in some modes of operation, for example, Galois counter mode, where we do multiplication in the finite field of size 2 to the 128. So moving on to instructions and pipelining, if we think about how instructions are executed in a CPU, so I don't have the pointer now, but what I wanted to say is this figure is supposed to indicate 4 different instructions that we want to execute. And in this case, we are executing them serially. And typically, these instructions are composed of different stages. So these stages can be, for example, fetching instructions and executing, writing back to registers, and so forth. So for this example, we have 4 different stages marked in 4 different colors here. And basically what we see is when we have serial execution, we first have to completely finish executing one instruction before we can continue with the next one. Now, this picture is very different if we have an instruction pipeline available. So basically what we see in this case is that the different stages for the different instructions are still performed sequentially, but in fact we can have different instructions being in different stages of execution at the same time. So we greatly reduce the overall latency of executing these instructions. Now, of course, this is only something we can do if we have independent instructions. So if you compare, for example, to CPC mode and encryption, we can't do this because, as I just said, we have to finish encrypting one block before we can continue with the next one. 2 important parameters that I want to briefly mention of instructions are the latency. So the latency in this case is 4. So this is the number of cycles that we need to wait before an instruction is finished. And also the inverse throughput, which measures the number of cycles we have to wait between issuing instructions. So in this case, this inverse throughput is 1, meaning that we can issue one instruction on the pipeline every clock cycle. If we look at how these ASNI instructions look like with respect to latency and throughput on Haswell, we see that on the left-hand side here, arguably the most important instructions, the encryption operations, all have a latency of 7 cycles and an inverse throughput of 1 cycle. But this means also that serial modes of operation are severely penalized because every time we issue one of these instructions, we have to wait 7 cycles before we can issue the next one. But in fact, from the inverse throughput, we see that we are able to issue one instruction every clock cycle, which means we are wasting basically a lot of time in these serial modes. So the question, or what we actually have to do is, if we want to speed up serial modes of operation, we have to look somewhere else for independent data to operate on to fill the pipeline. This brings me to this picture. So this is a bar chart showing how packet sizes are distributed on the internet in 2012, so a fairly recent study. And what we basically see here is that about 44% of packets are between 40 and 100 bytes in size, and about 37% are between 1400 and 1500 bytes in size. And then the remaining 19% are somewhere in between. Some are a little bit longer also. And the implications of this is, of course, that we don't really see these very, very long messages that people sometimes use for benchmarking in the wild. In fact, what we do see is that we have many smaller messages available, and these tend to be highly clustered. Now, what can we do with this? Well, if we combine this observation together with the fact that blocks of data from different messages are independent, this means that we can probably use this to speed up the sequential modes of operation by processing these independent messages in a pipeline. So let's try to look at how to do this. So with this picture, I wanted to show CBC encryption using the AS/NI instructions in a pipeline. And here we're considering 7 different messages, so I have given them different color codes here. So this again repeats the pipeline picture from before. So what we see is I start to issue the instruction for the first round of encryption for the first block for the first message. So basically we are issuing the instructions in a message first order, and then round second and block third. So essentially this picture shows us that once we are done completing the first round for the first block of the first message, because of the latency of 7, we can immediately issue the next instruction that performs the second round of this block. Now we continue with this for 9 more rounds, and what we get is immediately that we have encrypted the first block for 7 different messages in parallel. Then in CBC mode, what we do is, of course, we XOR the ciphertext to the next plaintext block, and then we can start doing the same thing all over again. So this picture continues for a while. But of course, what we don't see in this picture is that messages tend to have different lengths, right? So we're not in a scenario where all messages sort of end at the same time. We saw this with the previous picture of the distribution. So this means that at some point, these messages are going to run out of message blocks to encrypt, and then we have to do some scheduling operations associated with determining which messages are done and what we still have to do. So these scheduling decisions lead to pipeline stalls. This is, of course, something we don't want to do or to have. So the question is, what happens when we have these different message lengths? And this is what we try to attend to in our paper. So the scenario is that we have different messages, all of different lengths. And the problem, as I just mentioned, is that we don't immediately know how these scheduling decisions are going to influence the pipeline, but it will lead to some kind of pipeline stall where we have to choose what to do next. So in our solution that we call comb scheduling, what we propose to do is to do all of these scheduling decisions as pre-computation. So this means that we always consider messages in windows of width p. So in other words, we look always at p messages at a time, and then we do the pre-computation based on these p messages individually and independently of all the other messages. And inside each pre-computation, we process messages in a greedy fashion, and this solution works for any message distribution, also including this bimodal distribution that I showed before. So I want to give an example of how this pre-computation works like. So let's say we have a window of size 7, so we're looking at 7 different messages in parallel, and these 7 messages all have different lengths. So this is these here are typical lengths sampled according to this bimodal distribution that I showed before. And I have written these messages M1 through M7 here with their respective block lengths in 128 bits. And the blocks sort of go down, and we're interested in processing these in, for example, CBC mode. Now, the first thing we do for the pre-computation is to sort the messages. So we sort them according to decreasing size. And now what we want to do is we want to pre-compute what we call sub-windows. So I will be writing those over here in this right side. And basically these sub-windows, they consist of the pre-computation that we want to do. Now the observation that we start out with is that all messages have at least 7 blocks of data to be encrypted. So the first sub-window says that basically we have 7 messages that we want to encrypt for 7 blocks. Now, after we have done this, we know that the shortest messages, namely M2, M3, and M4, will be completely exhausted, and we have to continue now utilizing the pipeline in a less optimal way because we only have 4 messages at the same time. But these 4 messages, on the other hand, we have for 80 blocks until the next message is exhausted. So at this point, we are able to really use the pipeline for a long time without any scheduling decisions. And after we have done this, then we know that M5 is now exhausted, and finally, in the end, we have just 3 messages with 9 blocks remaining. And so these sub-windows over here basically comprise all of the of the pre-computation, and this basically says how we should schedule these messages for the pipeline when we are doing the CBC encryption in this case. So this leads me to some performance data. So this table gives performance for CBC encryption on Haswell. And the first column that we see is the serial mode, the serial column here. And what we see is that, So the first column is the serial performance, and then the other columns give performance data with varying window sizes between 2 and 8 messages at the same time. So the first thing we see, if we look at the first 2 rows, so the first 2 rows of data give data points where all messages have the same length. So all messages have a length of 2 kilobytes in this case. And comparing the serial performance with the performance using a window of size P, we see that we're able to reduce the performance from 4.4 roughly cycles per byte all the way down to 0.66 cycles per byte. And this means that in this case, actually, CBC mode is performing almost as good as ECB mode, which I think is quite nice. And for this fixed length scenario, we have about a 5% increase in latency. And this is something we pay in turn to get a speed up of about 6.6 times. If we then look at the last 2 rows of the table, this is where message lengths are now sampled according to this this realistic distribution, and of course we expect this to perform less well compared to this ideal case of equal length messages. But what we see is now we have an increase in about 39% in latency, but we still get about 5 times speed up. Now if we compare the throughput between those 2 cases, we see that in the realistic setting we are within about 10 to 30% of the optimal speed up. I included this table also because I know a lot of people are interested in the CSOC competition. So we took also a lot of authenticated encryption modes based on the AS, and we implemented them first sequentially, and also for the sequential modes, we implemented them using the comb scheduling, using a window of size 7. So this gives here the sequential performance, and then also the performance using our method, and the relative speed up. So if you're interested, you can look in our paper and have a look at some of these numbers in detail. So just to conclude in the end, what we saw is that on the internet, actually realistic traffic is not very long messages, but we tend actually to have many, many smaller messages that are clustered. And this means that we get a source of data independency that we can draw on to be able to speed up serial modes of operation, such as the CBC. And this is exactly what our proposal does. And we see that the performance that we're able to achieve is actually quite competitive to the parallelizable modes. Now, some of the future work that might be interesting to look at would be to implement also this comb scheduling for parallelizable authenticated encryption modes. So these are modes that typically have some sort of serial processing to them, especially in the initialization and tag generation. And we believe that for very short messages, it's possible that, that the comb scheduling might be able to improve performance in this case. And also looking at longer windows or also dynamically adapting window sizes might be interesting, especially in, for example, web server applications where the load is typically not the same at all times of the day. Also, I just want to mention briefly in the end that we have applied for a patent on this approach. And if you're interested, you can come and talk to either me or my co-authors more about this. So thank you.
Any question? Yes, was there about?
Of course, fast encryption in hardware is not something new, or decryption. And so these schemes were suggested in several papers in the 90s. It's in an ISO draft already in early 2000, and the ISO standard allowing this option is in 2006 published. But it's not, of course, it didn't do the AS&I work. It's very nice work, but the idea of having parallel CBC instances is actually quite well known.
Okay, in hardware or software or?
For both.
Okay.
Any other question or any other anteriority? Okay. So maybe I have a question. So I guess that this makes sense only when you have several messages to encrypt, right?
Mm-hmm.
Yes. So if you have a single message, so we are back to the figures of 4.3 or 5.5 or?
Mm-hmm. Yes.
Yeah. Okay. Other questions? So let's thank the speaker again. So now we have